So, as I said, my hope is, and Lisa and Jason will have to sort of keep their eyes open, because I can't necessarily see hands up or anything like that. But I just want to sort of foment some discussion here as to what can typically multi-collector sort of isotope ratio mass spectrometry, but also something we've heard a fair amount about today is using like quadrupole and high precision or ICP-MS for getting concentrations, elemental concentration values as well, which I think are both important. Some of the bullet points I put here, like, for instance, the first one, with mass spectrometry, you do have the ability, as has been mentioned earlier, to measure both the stable and the radioactive nuclides in a material. For somebody making radioactivity measurements, that may or may not be important. But sometimes people do want to know what other contaminating elements are in a material, or what is the isotopic composition of the particular element that has that radionuclide. Another topic might be, clearly, and we've seen examples that can be very useful for measurement of long half-lives, where looking at sort of the decay over time really isn't feasible for getting a half-life value. Obviously, its primary use for multi-collectors is the precise measurement of relative abundances. And just real quickly, also, and I think Mike Winchester talked about this, precise measurements of absolute amounts is another capacity, but that requires something that we'll probably get into more. For isotope dilution, you have to have calibrated materials. So I see that there's something in the chat. Okay, this is a reference to something else. And this, in some cases, is what I refer to as potentially fewer corrections. I think, again, it's been noted in a lot of these talks, when you're using mass spectrometry, you do have essentially mass-dependent fractionation. And sometimes that can be quite hard to characterize, and typically it's done by calibrating with a known material. But some of the other corrections that are frequently have to be used in radioactivity measurements aren't necessarily there. We have different interferences in mass spectrometry, and also efficiencies aren't handled in the same way, since we're counting ratios or calibrations against some sort of intensity concentration curve. So anyway, that's sort of enough of an introduction from me. I'd really love to hear from some of the people on in the meeting today. Are there particular advantages or things that you might like to talk about or know more about, might be a better way to put it.
Thank you, Richard. No hands yet. So let me ask you, when it comes to sample preparation, I see Karsten has his hand up. So Karsten, you go. Karsten, you're muted. I can't hear you. No, still no luck. Perhaps you can put it in the chat. Yeah, and while you're typing, I will ask, when it comes to sample preparation, are there significant advantages or disadvantages between the two techniques? The two techniques being mass spec approaches versus our usual radionuclide metrology approaches.
Well, I think that's actually a very good question, and it, like a lot of things, the answer is it depends. Certainly for mass spectrometry, one of the things that is almost necessary for any kind of high precision measurement, specifically for isotope ratio mass spectrometry, is you want to have very clean samples to minimize interferences and also enhance your sort of signal intensities. So the preparation for some types of mass spectrometry, particularly for thermal ionization mass spectrometry, can be quite extensive. Where obviously for something like gamma spectrometry, my dog is announcing his presence. For something like gamma spectrometry, you may not need to do any sample prep at all if you're just sort of doing a bulk measurement.
I see, thank you. Karsten's question is, well, it's more of a comment, but it's kind of a vague question. This means, as you've described the advantages, this means that half-lives are kind of like new standards, yes?
I'm not exactly sure how he means it, but but I think it's a fundamental point that having well-characterized half-lives, and I think there's another aspect of it is essentially traceably measured half-lives is the link between numbers of atoms, obviously, and radioactivity. And I think it's fundamental to using mass spectrometry for measurements of radioactive nuclides is the half-life, and I think in many cases we need more precise determinations of half-lives, which is kind of circular because one of the ways to get more precise half-lives is using mass spectrometry to get at some of these amount values. And another aspect of that is making these half-life measurements with real sort of clear traceability chains.
Thank you, Richard.
I don't know if that spoke to
yeah, so Karsten, if I see Zoltan has his hand, but I would like to make sure that that kind of addressed Karsten's question, comment. You can put a thumbs up, Karsten, if yes, or maybe a thumbs down if no. While he's figuring that one out, Zoltan, you have your hand up.
Richard, I just have coming in as a chemist and mass spectrometrist, can you speak a little bit about the practical or useful uncertainty regime where CCRI usually operates? So what are the uncertainties what the CCRI community or stakeholders are looking for? In chemistry, we work usually in the low percent in the isotope ratios in the low per mil or sub per mil range. So where these radiometric measurements or typical measurements operate? So are there potential synergies?
It depends a lot on your sample. So when it comes to our primary measurements, we are at K = 2, we're at as low as 0.5. Uncertainty of 0.5 all the way up to maybe 1.5 or 2. We're very, very tight on the primary
percent.
Yes.
Yes.
0.5%.
Yes, percent. We're very tight on the primary measurements. But when it comes to matrix-based measurements, such as gamma ray spectrometry, which Richard mentioned earlier, requires relatively little sample prep. It can be quite high, up on the order of almost up to 5%. Richard, would you agree with that?
Yeah, I mean, it's certainly consistent with what I've seen, and again, I think this is something we'll get into more, is that sometimes some of those uncertainties in the activity measurements are driven by things that could be improved with mass spectrometry.
By mass
Sometimes,
spec, yeah, that's what
so
I was
like-
getting at.
like corrections for interfering isotopes is a good example.
Or half-lives even.
Yeah.
Yeah, because a lot of the uncertainties in those primary measurements are coming from the decay data that are used in the determination.
I guess Simon has his hand.
Yes, Simon has his hand up. Simon.
Yeah, for example, better half-lives for plutonium-242 and thorium-229 would be a great help.
Yes,
A comment.
you're right.
It really does depend on what you're trying to measure and the final purpose of your measurement.
Like in the chemistry regime, we're always looking for fit for purpose, right? We want to make sure that our measurements serve the community for which we are doing the measurement.
Exactly, yeah. I mean, work I'm involved in, some of it, we need to show that plutonium-239 to 240 ratios can be shown to be from the fuel cycle and not from military use of plutonium. So better half-lives helps all that. Just a comment.
No, thank you, Simon. A very good comment. So Dante has put in the chat, uncertainties in branching ratios can also dominate the budget in gamma X-ray spectrometry isotope ratio techniques.
Yep. Yeah. I suppose this is sort of, I'll touch on that a little bit, is there's, I'm forgetting off the top of my head, but there might even be opportunities for well, not so much in energy branching ratios, but in complex decay schemes for mass spectrometry. Sorry, I'll maybe elaborate on that a bit more later. One thing I want to also bring up is the sort of flip side of this. And then maybe this is something that other folks will want to sort of touch on a bit, and that's what are the sort of the places where mass spectrometry falls short, or maybe a better way to put it is how can radionuclide metrology, classical counting methods, maybe help out in terms of mass spectrometry, isotope ratio type measurements, or measurements of nuclear materials, for instance. I mentioned a couple things here is, for a variety of reasons, short half-life measurements, maybe they can be done, but they're difficult with mass spectrometry, particularly because you need to have a certain concentration of material to get high precision measurements, but you might be running into radiation safety issues to have enough atoms of some material with a very short half-life. Then there's the case where you're maybe looking at an isotopic ratio where you've got a very long-lived or even stable, and then you have a very short-lived isotope of that same element. So you have very large dynamic range in a material that you're trying to measure. Of course, anything with, this was also touched on earlier, elemental carriers can be a real problem. I think frequently when people are working with radioisotopes, they're using carriers for their chemistry. Well, that sort of creates significant problems for measuring those things by ICP-MS, because you've sort of saturated your sample with something that isn't of interest, and sometimes that can be you can get around that. But for instance, in a cesium sample, maybe you have so much carrier that we have to dilute a tremendous amount to be able to put it in an ICP-MS, and therefore the precision of your measurement of cesium 135 or 137 that you're interested in is hard to do by mass spectrometry. Another thing I sort of mentioned here is that there's a lot of elements that clearly we're interested in for radioisotope measurements, but there aren't calibration standards for them. By that I mean isotopic standards or spikes that are certified for amount and isotopic composition. And in some cases, the enriched isotopes different from the one that you're looking at just don't exist, or they're not commercially available. So, and these are just some of the difficulties that might be associated with using mass spectrometry on radionuclide measurements. And again, if there's other issues that people have encountered or interested in, this would be a good time to maybe bring those up.
Yeah, I think we saw in at least two of the presentations, we saw that from the CEA and from the NMIJ, we saw that the calibration standards isotopic spikes issue has come into play already. We're quite aware of that. I think one thing that would be useful for the radionuclide metrology community to know is what types of radioisotopes and in what forms that the mass spec community would like to see us try to work to develop to improve this particular potential disadvantage or this thing that's lacking in using mass spec for radioactivity measurements in general, not just radionuclide metrology. So I'm looking for more comments, more hands. Boonkin, you've got your, oh, I see. Raphael, you have your hand up.
Yeah, I'm not sure. I think it's more of a statement. I think Hélène's presentation was excellent in that it showed the we're talking about the two communities working closer together. The chemical preparation is critical to keep in mind both the mass spec world as well as the radiometric world, because they have complementary interferences. In the example I was giving with the protactinium, the sample was prepared at Lawrence Livermore National Lab, and it was perfectly suited for their application, whereas for the radiometric, there was this impurity that significantly affected the radiometric measurements. And again, it was hard to determine that after the fact. Whereas if you look at Hélène's talk, again, if you're working in concert, the radiometric preparation of the samples that you're both communities are going to be measuring, there might be other considerations to take into account. And I would also then point out again about the protactinium 233. That was again something that was not readily available, and perhaps could have been readily available if again the two communities had better communication, which I think is already paying off.
Very good observations, Raphael. Zoltan, you still have your hand up, or you have it up again?
No, it's again. I was just contemplating on the calibration and standards issue. Maybe it's an opportunity also to think about potential collaboration and co-fertilization of these two fields, because basically in the chemistry side or in the mass spectrometry side, if I want to be blunt, none of our measurements are absolute. So as Richard correctly pointed here, out. We need standards for physical standards, physical artifacts to calibrate against, and the radiometric community have access to primary or semi-primary approaches to potentially create standards for mass fraction or isotope ratios. So that might be an input to the chemistry world from the radiometric world, helping calibrate our mass spectrometry approaches.
Thank you. Thank you. Anyone else?
Mike has his hand up.
Oh, yes, I didn't notice. It just came up, Mike. Go ahead. We don't hear you, Mike. No, I'm afraid not. I can read lips, but no. Okay, thank you.
So maybe while Mike's typing something, there's a point, and I think we'll probably touch on this more in a discussion tomorrow, is issues of traceability. One of the things that we saw in at least one of the talks was using sort of assumed or like IUPAC values for what the natural isotopic composition is of some element that we use to calibrate for mass spectrometry. These are essentially evaluated data values, but they have in nature frequently these vary. How does that factor into the traceability of a measurement? And again, I think this is foreshadowing a discussion that might be in more detail tomorrow. But these are some of the issues that I think we've run into, because like for uranium and plutonium, they make synthetic calibration and other elements, synthetic calibration mixes where you can use gravimetry to essentially mix isotopes. But there's an awful lot of elements where that can't or hasn't been done yet. So you're sort of stuck using assumed natural compositions for calibrations.
Thank you, Richard. So Michael's comment is producing calibration standards for mass spec for radionuclides has the complication of instability through radioactive decay. I would say duh, but yes. So anything would have to be adjusted over time based on half-lives, which would raise the uncertainties, of course. I think those are very good observations. During the discussion, I thought of the perfect technique to develop would be live time mass spec. So basically you can see the decay of the curve as the source is decaying away. Of course, you can do that, but it's always a kind of a step function. You can't actually follow. I don't think you can actually follow the decay of a curve. Or is there a lifetime mass spec technique available?
Actually, that's something that Lisa mentioned was something I've thought about a little bit, but not really put a bunch of time in, is that for measuring very short-lived isotopes, would it be possible to use a mass spectrometer and essentially input the particular nuclide into a detector and then watch it decay in that detector, use essentially mass spectrometry as a separation technique? I think that is done in some nuclear data applications. I should mention that Mike has another comment.
Yes, thank you.
And I don't know if you want to read that, Lisa.
All right. Many calibration standard producers need to recover cost, which makes this more difficult to sustain economically. This is true. Money always comes into play, but I don't know what to say to that. It's true. And Simon has added a comment. Certificates for radionuclides state the activity concentration at a stated time, so the connection is made by the user. The correction is made by the user, and that's true. I think an issue is when you are doing the mass spec measurement, especially if the half-life is quite short, because the measurement itself takes some time. It may be more difficult to get the precise ratio you're looking for at a specific time.
Yeah, and I think for things with moderate, I don't know if that's the right word, half-life, something like cesium-137, where you've got a 30-year half-life, so it's not sort of decaying away so fast that you can sort of watch it while you're doing mass spectrometry. But over the course of years, that uncertainty in the half-life is starting to blow up the uncertainty in the isotopic ratio as more of it decays away.
Yeah. So let's see. Any further? So Dante has added a comment. The neutron activation analysis community might have insights into real-time mass spec measurements for short half-lives. Oh, that's a very good point, because they do need to worry about that sort of thing. Thank you. Very helpful. Young-Suk, you have your hand up?
Yes, I also wanted to mention one thing about the relation with these two areas. I think that we need a kind of some intercalibrations between measurements in the radiation field and the amount of substance field or the mass field, whether the data can be really comparable between each other. I think that we know that for example, that already I mentioned about the activity concentration and the mass can be comparable between these two techniques. It can be reproducible and also some consistent with each other. Then we can use those two techniques for these radionuclide measurement. Yeah, just a simple comment.
Thank you. Thank you very much.
And to amplify that, something that actually, when Jackie Mann and I have conversations, something that frequently comes up is that we would love for like the spectrometry standards that NIST produces, the single element assay standards. There's a lot of people who would love to have certified isotopic ratios for that. Mm-hmm. Likewise, for our single element activity standards, there's a lot of people who would like to have concentration and isotopic data on those. But as Mike Winchester pointed out, those are resource intense measurements that would require a very significant investment of resources that we possibly can't recover the cost of.
I'm just going to pipe. This is Jackie. Richard's bang on right, and we've heard from many of customers for years. Why can't you assign isotopic values to the spectrometric solutions? The challenge with that, a lot of the spectrometric solutions, were not made for that community, like the current ones that exist. So we really would have to kind of start from scratch to create like a suite of the spectrometric solutions specifically for the isotopic community. Otherwise, we could have a situation where we end up selling out of everything and then there's nothing left for everybody. So we have to be careful with that.
Wow, sounds like an excellent role for a surf student over the summer to get that started. So Mike, before I get to you, I see your hand is up. Simon has a very good point. You can, of course, correct for decay during the measurement using the decay equation over the measurement time. I think, though, in mass spec, unless you have a very well characterized instrument, it's not. I don't know how precise the timing of the data output from the mass spec might be. So, Michael, you've got your hand up, and
can you hear me this time?
Yes, we can. Thank you.
Okay. Yeah. Somehow my microphone setting got changed. So it was using a microphone that didn't exist. Okay, so back to the spectrometric solutions. This is a good opportunity to make one point about those, the SRM 3100 series. We see this happen a lot. Those are produced in the group that I lead here at NIST. And we see those used as isotopic standards a lot because there isn't anything else. And folks take a particular SRM in the 3100 series, measure the isotopes, and then they use it that way. And this is the point I want to make. That's fine so long as that particular lot number is available. But what happens then is that when it sells out and we create the next one, we don't make it with isotopes in mind. And so we may change source materials. And when we do that, the isotopes that were measured in the previous lot will not apply. And so, we have folks that want to ask us about the isotope abundances in a particular one, and we haven't measured it, and they're really not intended as isotope standards. And when they're used that way, you have to realize that they're only going to last as long as the lot does. So I take the opportunity to make that point to this community.